There we go.
Tell you what I could use this morning. Oh, shit. I should have snuggled in. That's what I was about to say. Yeah? A little bit small. Okay. Maybe perfect, right? The book you overstood? Yeah, you know, I'm just growing a lot with this. This one's just this is coming too.
Estimated time on the other one.
It actually takes a while. So to like actually wrap your head around it, it just takes a lot of time sitting there having no fucking idea. But you literally have to the whole thing.
I don't understand.
Because it really is interesting, and honestly kind of satisfying.
Oh, signals?
It's just kind of first time.
Thanks for coming to class. I don't know what it's about.
It took us like 3 or 4 hours. It's probably about 2.5 to do the first 3 problems.
But no, something.
I was so happy when I saw last week that there wasn't anything to other people said, just for it to be just try it out. Yeah. Morning.
Good morning. So, raining quite heavily outside, and yeah, and it reminds me of something. When I was very young, like real young, my most favorite class was drawing. You know, when people are very young like this, they have a regular class of drawings and arts and stuff like that. So that was my most favorite class. And at one day, it was raining extremely heavily, like raining cats and dogs. But I didn't want to miss that class. So I went there all out just by walking because there was nothing out there, no vehicle. Because I didn't want to miss the class. It was so interesting to me, drawing stuff. And when I reached there, voila, nobody was there, not even the teacher. So I felt so cheated. That man, it never occurred to me that a teacher can miss the class. I always thought it's the student. So anyway, I mean now I'm in the opposite side of the classroom. And I'm hoping that I will not repeat what my teacher did in that class. So thank you so much for showing up. We'll have a little bit of discussion today, just some repetition of what we did already, and so that it helps you in the exam. Today we will also have our regular office hour. Okay? So please utilize that office hour. If you have any questions, please show up and we'll discuss. So, let us begin with something that's very simple. The calculation of divergence. So we say that the divergence of a vector field, let's say our vector field is an electric field, and you guys check if the camera is on. Is it on? This is getting the entire picture. Oh, thank you. So let's say our electric field is like this. it has two components, x and y component, and each of these components has some coefficients. Then the divergence of these fields would look like the following. We have to take the partial derivative of the x component of electric field with respect to x. And similarly, we have to take the divergence, the differentiation, partial differentiation of the y component of electric field with respect to y. And then we have to add up all those components together. So since you already know how to do the differentiation, the answer of these things will be the following. You have to differentiate e to the power twice x. So let me write it explicitly. And then the answer will be the following. So this is the divergence of electric field for this given expression. If I ask you to evaluate this divergence of electric field at any arbitrary point, let's say at a point where xy is 1, 1. So in that case, the divergence of electric field at the given 1, 1 point will be So this means if we evaluate this expression into a coordinate where both x, y, z have a value of 1, 1, and 1, then this will be the final result. The divergence of electric field will be 2 squared plus 1. Right. Does anyone have any questions at this point? It should be very straightforward. Still, if you have any questions, please. Okay. Alright, so I'm guessing that everyone understands up to this point. Let me ask you one more question. I say that in order to find the divergence of electric field at this 1, 1, 1 point, I took the original expression and did the differentiation to get up to this point where I have all these variables x, z, and then I plug in the value of x, y, z coordinate to get to this point. Right? What if I plug in all these values here first and then do the differentiation? Will I get to the same answer? Let me repeat what I said. I say that in order to find the divergence of electric field at 1, 1, 1 point, I first took the original expression, did the differentiation, and then plug in the values of x, y, z. But what if I do the plug-in earlier? What if I take the value of electric field and plug in the value of 1, 1, 1, all in this first expression? If I do that, my electric field would look like the following. At a point where x, y, z is 1, 1, 1. Do you follow? If I plug in this value as the original expression, I should get the following expressions of electric field, right? So, if I take the differentiation, if I take the divergence of electric field like this, Would I get to the same point? No. In fact, it's just 0, right? It should be just 0. So why it's like that? Why it matters? Whether I put the plugin in the original expression or in the final expression. Why does it matter? Any thoughts on this?
Because
Go ahead.
You're given the point for divergence, not the electric field. So it doesn't make sense to plug in one's for that you're getting for divergence that you're trying to find for divergence and plug it into the electric field and then consider it.
Okay. Any other thought?
Well, yesterday we talked about when we had like a point, there was no charge density there, so the divergence electric field was also 0. So that's kind of where this is coming from.
Yes, I'm just going to change the next section that one takes
Okay, so you're talking about the charge density. This is true for electric field, but even if it is not an electric field, let's say it's any vector, any arbitrary vector, but we have no relation to electromagnetic. Can you still plug in the value first and then do the differentiation? No. So it has no relation with charge. It's simply, in order to find the change of the values of the vector field, you need to keep all the expression intact, do the differentiation, and plug in the final values. Because we are trying to see, let's say this is our plane, and on that plane, maybe our electric field looks like the following. So, if we try to find out the corresponding change of electric field at any given point, we need to know how electric field is on the left-hand side and how the electric field is on the right-hand side. Not exactly what is the electric field at this particular point, because the differentiation means how the electric field is changing around that point. Okay? How the electric field is changing around that point, particular point. That is your differentiation. So, if you just plug in this value, let's say 111, exactly, let's say I want to find out the divergence of electric field at this particular point. This point is very small. The box that I drew here is very small. So if I simply plug in this 111 value here in this original expression, yeah, sure, I will get the value of electric field. But that's not what I'm interested in. I'm trying to find out what is the change of electric field around that point. So if you really have to plug in, you do not need to, you shouldn't plug in the value of 111 in this expression. Rather, you may do the following. You may plug in a value right here on the left hand side, on the right hand side, and right here on the left hand side. So instead of having a plug in a single value, you might plug in the value at its neighborhood. And then you see what is the difference. Then you will get something that is very close to your actual differentiation. Okay? So in other words, if you really have to plug in, maybe, let's say that somehow I forget what is the exact process of differentiation. But I know that I need to find out the change of electric field. So I can do the following. I can take the expression of electric field, and maybe I can just plug in the value of electric field, not exactly at 111 position, but maybe at its neighborhood. Let's say I want to plug in at 11.9. There's something which is very close to it. You get a value. Let's say it is right. This is how it will look like, right? At a point which is very close to it. You do the same thing for another neighborhood. Maybe this time you go to the other side. Instead of having a value which is less than 1 for the z value, z axis, you take a value which is 1.1, a little bit higher than the original point that you are interested in to calculate the differentiation. And you calculate the corresponding expression of electric field. So this time, I will have a value which will look like the following. Right?
Would it be y hat?
Oh, I'm sorry. Thank you so much. And then you take the differentiation. That means you see that how exactly the change is happening. So I can take these two guys, let's say this is E1 and this is E2. E1 is evaluated at a point which is not exactly at 111, but something very close to it. E2 is also evaluated at a point which is not exactly at 111, but something close to it, at a different direction. And then I take the change of electric field and see how fast the change is happening. So I take the difference between E1 and E2, and I divide them by the change of the value of Z. Because I am changing the value of Z here, right? Everything else, the value of X remains as 1, the value of Y remains as 1 for both E1 and E2. The only change is the value of Z. So this is why I take a difference of Z, I take a difference of E2 and E1, and I see how fast the change is happening. That might give you some answer which is something close to this original expression. Okay? However, remember that this is a two-dimensional problem, so this is a three-dimensional problem. So maybe instead of just having a Z, you also want to see what is the change of X and what is the change in Y. Okay? So this is how, if you really have to plug in, you have to plug in the value in the neighborhood, not exactly at the original point. You see what I'm going on? So please always keep that in mind. This is something very basic, which may be helpful for many different topics, not only in electromagnetics. So differentiation, the takeaway from our discussion is that differentiation always care about what is going on in the neighborhood, not exactly what is going on at that particular point. Do you have a duster? Alright. This time, we try to find out the divergence of an electric field that comes from a charged sphere of a Van de Graaff generator. So, this is the Van de Graaff. We have charges on the surface of the sphere, and we know that this guy is going to have a radial electric field all around itself, and we try to find out the relation of electric field with respect to space. So if this is the center of the sphere, and let's say this is the origin, so it is 0, 0, 0 point, and we want to figure out the electric field along the x-axis. This is y and this is x. The electric field is 0 inside the sphere, and electric field shoot up, become the maximum at the surface of the sphere, and then it gradually went down. This follows the relation of 1 over x square outside the sphere. This is what we discussed also, right, yesterday. Alright. So, we wrote the expression of electric field as the following way. we say electric field is kq over r square with a vector r hat. This is how the electric field should look like outside of the sphere. So this is the sphere. And then we try to see what if I replace the value of r hat and r square with x and y coordinate. So the value of r hat can be written as cosine theta x plus sine theta y, and r can be replaced by x square plus y square. That is what we wrote yesterday on Wednesday. And we try to see that what is the divergence of electric field at a point which is outside of the sphere. So this means that we have to take the differentiation of this guy with respect to x and y. So take the differentiation ddx of Ex and dy of dy and add all of them together. And before doing the differentiation, we say that we are sure that if we take this value of differentiation, if we take the value of divergence at a point outside of the surface of the sphere, the value should be 0. Why? Because it follows from Poisson's law of electrostatics, which says that the divergence of electric field must be equal to rho over epsilon, where rho is the charge density. Everyone follows? So, if we talk about a point which is outside of the sphere, we know that outside there is no charge. That means charge density is 0, and that means divergence of electric field must be 0 outside everywhere, except on the very surface where we have charges. So, if we take the differentiation for this guy, we should get a value of 0. I ask you guys to try it out in your computer to see whether Mathematica or Wolfram Alpha can give you a value of 0. Did you guys have a chance to try it out? No?
Yeah, a lot of us couldn't.
Yeah, it doesn't work.
You couldn't get it?
We couldn't get 0.
So you tried it?
Yes.
You tried it?
Yeah.
Okay, very good. I'm really happy that you gave it a try. So let us see what went wrong. All right. So I'm using Mathematica to figure out that what should be the divergence of electric field at a point outside of the sphere of this Van de Graaff generator. And let me write the expression one more time on this board so that we can see whatever we write it here and we can compare it. So we know the following. We say the electric field is kq divided by r square, and it has an x component and a y component. Cosine theta of x and sine theta of y. the value of r square is actually x square plus y square, and cosine theta is actually x divided by root over of x square plus y square. Similarly, sin theta is y divided by root over x square plus y square is a y hat. That means I can simplify. I can say that this entire stuff is x divided by so this is what we wrote here. I just repeated the same equation on this board. And the way we can solve this equation in mathematics is the following. We define a vector, which is f1 here, and we define the x component and y component for this vector. So the x component is x divided by x square plus y square raised to the power 3 by 2. This is exactly what I wrote here as the coefficient of Ex, right? And this is the y component of the electric field vectors. This is exactly what I wrote here, right? So let's use this guy and see what if I take the divergence of these f1 vectors and evaluate the divergence of f1 at a point outside of the sphere. So I took the differentiation, I took the divergence, dIB is the common, and I evaluated it at a point x2, y1, and look at the value. It's not 0, right? So when you try it out, you actually were not correct. I mean, you actually were not wrong. It was not 0, okay? So something is wrong, right? We say that if the electric field is taken outside of the sphere, there is no charge. That means there cannot be any divergence of electric field. That means whatever comes in is whatever goes out, right? There is no water sink or there is no water sources. But this guy says it's not divergence. It's not a 0 divergence. So something is missing here, right? And let us try to understand what is missing. So in a sphere, do we have only x and y components? We have 3 components, right? X, y, and z, right? So this means, in order to fully evaluate the value of electric field, you should include all these x, y, and z components. So if you add all the z components in this expression, can you make a guess like how it will look like? Instead of doing the math, maybe you can use some simple rationale, like it's adding up x plus y and y square, x square plus y square. If you consider one more dimension, like z axis, you have to add one more component here, one more term, z square, in both x component and y component. So this is what is done on the very top side. Do you see this? The x vector says that it has 3 components, x, y, z. And look at the denominator. Instead of x square plus y square, I wrote x square plus y square plus z square and raised the entire thing up to the power 3 by 2. You see this? So it's simply we are adding one more component, z, in this entire expression. And then you take the divergence of it and evaluate the divergence value at any point. What is the result? It's just 0. Okay? So that part was missing. The z part was missing. So look at that. If your dimensionality is wrong, then you won't get the right answer. If you just drop the z component, your result is absolutely wrong. So when you evaluate something, make special attention that whether the dimensionality matters or not. So let us say I want to calculate the electric field for a sphere of a Van de Graaff generator on this plane of on the board. So let us say that this plane of the board is just x and y coordinate. The z coordinate is on normal to the plane of the board. That means on this plane of the board, the z coordinate is 0 everywhere. If this is really the case, then electric field can be evaluated by plugging in the value of z equal to 0, and you will get the right value. So let's say that I ask you to find out the electric field on this plane of the board. You can simply take z equal to 0, use this expression, you will get the right value of electric field. Okay? You get the right value of electric field. You don't need to consider the z coordinate at all because you are just considering the plane of the board. But if I ask you to find out the divergence of electric field, divergence means it's differentiation. So when you do the differentiation, you cannot simply plug in the value of z equal to 0 in the electric field and then do the differentiation. You will be absolutely wrong. The correct way of doing it, take the whole expression of electric field, do the differentiation, and then you plug in the value of z equal to 0. Only then you will get the right answer. Do you see what I'm driving at? So it really matters that when exactly you are plugging in the value. If I ask you to evaluate the value of electric field, one more time, if I ask you to evaluate the value of electric field at an xy plane, which has z equal to 0 everywhere, you can directly plug in the value of z equal to 0 and get to the right point. If I ask you to do a differentiation of electric field, like divergence of electric field, you cannot plug in the value of z equal to 0. Although you are working on just x and y plane, you cannot take z equal to 0 right away. You have to keep the value of z component and do the differentiation and then finally plug in the value of z equal to 0. Only then you will get the right answer. Okay? You follow? So this is why, look at this. If I plug in the value of z equal to 0 on the very first line, I should get exactly what I get here. Right? Exactly what I get here. Because z goes up, z vanishes, the last component, this also vanishes. Whatever remains is simply the x component and the y component with z equal to 0. But if you take the divergence of it, you'll get very wrong answer like this. This guy gave you a very wrong answer. Okay? So for the divergence, always start with the most basic equation and then do the differentiation and then plug in the final value. And why it is so? Because we say that divergence or differentiation does not mean that you are evaluating the expression at that point. You are evaluating the expression at the neighborhood of the point. So if I ask you to find the divergence of electric field at origin means at 0, 0, 0 position, I'm basically asking you how exactly the electric field is changing around the origin, not exactly at the origin. Okay? So you cannot just plug in the value of 0, 0, 0, that is origin, at the electric field and get the divergence. Do you follow? Okay. So now you know that why you didn't get the value of 0. Okay? So that was missing here. So I wanted to keep it as like some sort of brain exercise to you so that you guys figure out that what is going wrong here. Okay? If I gave it out the right expression from the very beginning, you might not even realize that what is missing here. So please take a special note that the true expression that we derived in the class last day, this Thursday, was actually missing a component. The g component was missing. Okay? So always keep that in mind. That divergence or differentiation, this means that we are looking at the neighborhood of a point, not at the point. All right. So one more time, and this time I'm going to write this expression in the proper way. This expression is okay as long as you are going to calculate electric field at xy plane where z is 0. This part is okay, but do not take the differentiation of this guy. You take the differentiation. If you have to differentiate, you have to differentiate the entire expression, which means full expression electric field. This is how the total expression of electric field should look like. Okay? One more time. If I ask you to calculate the electric field at xy plane, you don't need to care about the z coordinate. You can just plug in the value of z right away to be 0 and do the calculation of electric field. If I ask you to find out the divergence of electric field, you must be taking care of all the components, do the differentiation, and then plug in the values. Okay? Please don't forget that. All right. So I think we pretty much discussed what I wanted to touch base on. I want to take questions from you guys. Do you have any questions that may require some more explanations? Any questions? This is the time. Yes, please. Not only on these topics, but any topic that we have covered so far, especially for the exam.
I did have a specific question that I did earlier with the just the first divergence calculation. What kind of, I guess, collection of charges could have an electric field that would give us that equation? Is there always?
You were asking about the very first method, like e to the power 2i6.
Yeah, so we know that the electric field due to a point charge will always have a specific form. So is there a general way to start with the electric field and then produce what the collection of charges looks like? I guess that's what my question really is.
Understood. I understood your question. And I think this is a very valuable question. So let me repeat the question one more time in my own words. And the question is like this. In the beginning of the class, we started with a arbitrary expression of electric field. We say the electric field is, let me write it here one more time. So we say that let us say our electric field is this, right? And we try to calculate what is the corresponding divergence of electric field so that we can figure out what is the charge at different part of this of the system. So the question, if I understand correctly, the question is that what kind of charge distributions can give you an electric field like this? Is that part of the question?
Yeah.
Right? So this is the question, that what kind of charge would actually give you this kind of expression? I know that if it's a point charge, then I'm going to get an electric field like this, right? What kind of charge distribution would give this peculiar shape, right? And the answer is, I do not know. Honestly, I do not know. And I'm totally pissed off when I see that people fight in their book hours after hours with arbitrary equations which has no real practical significance. So I just wanted to give it to you to make a point that when you differentiate, you do not differentiate at that point. You differentiate on the neighborhood. Only to make that point, I created this arbitrary shape. In reality, I don't believe that it's possible to create an electric field like this. Like the amount of effort you will make to have a charge distribution which have this kind of electric field is insane, and by that time, people will say that you're crazy. It has no real significance. So, the answer to your question is that it's completely arbitrary. Just think that it's just a mathematical exercise. Okay, just a mathematical exercise. So very general. It cannot be. It doesn't have to be an electric field. It can be any vector field. Okay, only mathematical. And I think your question has a second part also. Can you repeat that question? Like the second part, you say that, like,
a bit more generalized. Like, how could we figure out what a charge distribution looks like given the electric field? I guess whether it's possible or not. Like, could we figure out whether it can be physically possible? I guess.
Mm-hmm. Okay. So the way I see the question is the following: a little bit different wording I put. So let us say I know how to calculate electric field if I'm given a charge, right? I'll use maybe Coulomb's law, or I will use Poisson's law in order to figure out the charge distribution, and from the charge distribution I can figure out what is the electric field. But what if I'm given the opposite problem? Like, what if I'm given an electric field and I'm asked to figure out what is the corresponding charge distribution? And is it something practical? Like, in real life, would I really see a situation where I will be given an electric field distribution and I'll be asked to find out the corresponding charge? It seems very inverse problem. Does it really occur? The answer is this. So this is a story from one of my experience in industry. I'm trying to put it in a very simple way as possible. So we're trying to work with a device that's very small, and let us say that it is 100 nanometer in its size, and we knew that if I apply some voltage on these two metal plates, then this guy, after some certain point, this guy would break. Let me say explicitly what I drew here. So this is a metal. This is also another metal. And this is an insulator. The insulator is typically made of silicon dioxide for electronic chip. So we know that when we apply some voltage on these two parts of metal, it will create an electric field in between them, right? And we also knew that what is the safe margin of applying a voltage. You cannot keep applying voltage and increase the voltage continuously, because at one point of time, this guy will totally break. Remember that when we showed the Wilshire's machine, we showed that if you keep pumping that machine, at one point of time, it will discharge to the air. So air, despite air is an insulator, if you pump up enough voltage, at one point of time, air will give up. It will start to become a conductor, right? In a similar way, any insulator in the world can behave like a conductor if you pump up enough voltage, okay? So this is one of the very important questions that we often ask in industry, that how much voltage should we put in a device before the device breaks down? If let's say that we are working on this device and we have very high amount of voltage
on these two metal plates, then these guys will start to discharge through this insulator, and the device will totally fail, right? So we need to know that how much maximum voltage, Vmax, can be applied for a device like this. So there is a way to calculate that what is the safe Vmax value. Vmax means maximum voltage that you can apply. And we design the device, and then we figure out that whatever was our initial design from our calculations versus what we see from experiment is very different. This device was breaking much earlier than what we thought it would be. Okay? So our actual Vmax, let's say this is the Vmax from simulation. And this Vmax was much larger than what Vmax we got from experiment. And that's a bad thing. I definitely do not want this condition. In fact, the opposite condition might help us. My experimental Vmax is much higher than my simulation Vmax. Because that means my device is going to break much earlier than we expect. If you ship out your product, your customer will be very angry. He will come to you and maybe will kill you. So you cannot do that actually. So we have to figure it out, that what's going wrong. So we cannot see inside, right? But based on the value of Vmax, we actually can figure out what is the electric field inside, because electric field is simply the differentiation of voltage with respect to x. Okay? So if you calculate the voltage, you can correspondingly calculate the electric field inside your device. Okay? Now if you take the differentiation of electric field to find out the divergence of this guy, you will find out what is the charge here. Since our Vmax from the experiment was very different from the simulation Vmax, that means there must be some charge sitting inside. Maybe there are some charges. Maybe inside this insulator, maybe there are some charges hiding inside. And we cannot see it. There is no way we can see it. This is nanometer. And what is the size of the charge? This size, maybe this is an electron. So you cannot see an electron. But you can do the following. You can measure what is the voltage. From voltage, you can measure what is the electric field. From electric field, you might be able to measure what is the charge, because I know that divergence of electric field is actually the charge divided by epsilon. Right? So in this way, you can figure out that what kind of charge might be sitting on inside those devices. So those are the problems. And then you have to figure out some way to get rid of those charges. Okay? So sometimes it occurs in the opposite way. You are not given a charge distributions. You can only see what is the voltage. So from voltage, you have to figure out what is the electric field. From the electric field, you have to figure out what is the charge that is hiding inside those devices. Because there is no other way you can see the charge. Okay? Only that way you can have a guess at what might be going wrong. And then probably you have to also figure out what is the sign of the charge. Is it a positive charge or a negative charge? If it's a positive charge, then we have to figure out that what exactly we did so that it induces some positive charge. What kind of chemical process we did so that it induces some positive charge or not. If it is a negative charge, then our suspicion goes to the other directions. What kind of negative charge might be induced for what kind of process? So it's a very complex scenario, and it takes a lot of time. That's why I say that it takes an army to figure out what kind of problems we're dealing with. But eventually, this is what you are also going to do. That's why not all the time you'll be given a set of charge and you'll be asked to find out the corresponding electric field. Sometimes it's the opposite way. In fact, most of the time it's the opposite way. You have to find out the electric field. From that electric field, you have to find out what kind of charge is there inside. Okay? So Van de Graaff is something that is on a very large scale. In that large scale, charge distribution is very easy to see. On a very small scale, we cannot really see charge distributions. We have to somehow infer it from a very different experimental setup. Do you follow? Is my answer going too far away? Yeah, I'm sorry for that. But I hope that you got a little bit of insight of like what kind of situations you might be facing in real life. Like in real life, in fact, I like this question, the beginning question very much, because this kind of expression that I wrote here, electric field is equal to e to the power twice x with the x hat plus yz with a z hat. I do not think that this will occur ever. So it's really just a mathematical exercise. In real life, maybe something like this you would face in your daily experience, and you have to figure out that what is the corresponding charge density. Okay. So I think we talked enough. So it's time for you to have some rest. So good luck with your exam. If you have any questions, please stop by. I know some of you email me. I try to answer them as far as I can, but sometimes I miss it. So please don't be disheartened if I cannot reach out to you immediately. I'll reach out to you, but give me some time a little bit. And for the class quiz, I have not looked into the distribution of how did you get, like how well did you perform the entire class. I know that there are many people who have done very well, very, very well. There are some people who might be still struggling a little bit. It's okay. It's okay, since this is the first time we're doing something different. Really, we're trying to experiment a little bit. I know that not all the time experiment goes well, but I wanted to give it a try. Let's see how this goes. Because this electromagnetic course is one of the most difficult courses, one of the most notorious courses in an undergraduate for electrical engineering. You ask any person in this university, they will say this is the most horrific expression. Because there is a lot of math, and people, from day one, they totally submerge into mathematical expression and trying to crunch these kind of problems, e to the power twice x with x hat plus yz to the power z hat, with no understanding that what exactly is going to help. So I wanted to take a different route, like let us try something else. Instead of doing the mathematical manipulation, what if we build up our understanding from the theory very well, and then start to do our math. Okay. This is why if you look into our syllabus and compare it with the book, you will see that from for the last more than 1.5 months we talked about, right? So over that previous weeks, we have not covered too much in the book. In fact, yesterday I looked into the book and I figured out that I just covered maybe 10 or 15 pages up to this book. So it's not really much, but probably I talked way, way more than what the book actually covers. For instance, the book doesn't cover at all about the Van de Graaff machines, how exactly the electric field distributions would look like. But I thought it might be helpful for you to really see what is going on with some experiments. So I don't know, I mean, eventually this experiment may fail. I'm sorry for that. But I also believe that if you do not do an experiment, you cannot really improve the system. If people complain that this is a course that seems very hard and they really have no idea what to do with it in future life, that means something is very wrong. We have to take an action. So an action requires some experiment. Not all the experiment will be good. Maybe some of the experiment will be totally failure. But maybe something good will come out. So we'll see. Okay. Thank you so much for your time. And again, good luck for your exam.